En anglais, c'est ça? Okay. So, hello everyone. Thank you for coming. So today I'll try to make a rather short talk about this problem, which is the gathering of two mobile robots, which I studied during my master's thesis and during my PhD. So first, let us introduce what it means. So we're talking about distributed robotics. So distributed robotics is this idea that instead of solving a problem with one big complicated robot, we're going to use a lot of small ones. Obviously, this raises new problems and new issues that we don't have when robotics are not distributed. To model properly the robots we're going to use the Suzuki and Yamashita model that was introduced in 1999. And we're going to talk quickly about the environment, the robots themselves, and the synchronization. So the environment in which we are using those mobile robots is very simple. It's a 2D Euclidean plane, and there are no obstacles. So just an infinite 2D plane with no landmarks whatsoever. The robots themselves, well, obviously they are mobile, so they can move from one point to another. They are dimensionless, so essentially they have a radius of 0. They are oblivious, which means that they have no memory of past events. They are anonymous, so they have no distinguishing features, and they all run the same algorithms. They have no common coordinate system, which means that we have no common north, no common left and right system, and no common unit of measure of distance. They have no explicit way of communicating between each other, so no message passing or things like that. And the only sensor they have is a visual sensor that allows them to see where the other robots are. In terms of synchronization, we model the robots working in terms of phases. So the first phase they do is look. So they use that visual sensor to get a snapshot of the environment and of the other robots. The look phase is usually considered to be instantaneous. They also have a compute phase during which they make a decision as to what their next destination is going to be using the snapshot they just took. And then they have a move phase in which, well, they move to the destination they just computed. And after the end of the move phase and before the next look, they have sort of a waiting phase where they don't do anything. And the sequence of those phases is called a cycle. Now, we're talking synchronization, so obviously, we're going to have an adversary. We call it the scheduler. And the adversary scheduler has certain degrees of freedom depending on the model. The easier scheduler is called fully synchronous, where each phase is simultaneous for every robot. So they all look at the same time, compute at the same time, move at the same time. Then we have the semi-synchronous scheduler, during which the cycles are atomic. So essentially, the scheduler can choose to not activate certain robots at any given time. But it cannot activate a robot while another robot is already being activated. And then we have the asynchronous scheduler that basically has a lot of freedom and can just activate robots whenever it wants. We also consider the scheduler to be fair, so it cannot just forget to activate one robot. So essentially it means that there is no crash. We're going to talk a little bit about the move phase. We have two different hypotheses that can be used, which are called rigid and non-rigid movement. Rigid movement is this idea that the scheduler cannot interrupt a move phase. So if I have a target, I am going to reach it at the end of my move phase. The non-rigid movement means that the scheduler can actually interrupt the move phase. So this could be very bad if the scheduler could just start a move phase and interrupt it immediately after, then we would have no movement. So we have what we call a minimum movement hypothesis, which is called delta. And so the idea is if I have a target at a distance x, then I'm moving at most x, so that's the best case when I'm reaching my target, but I'm also moving at least a distance of delta. So the scheduler cannot stop me before moving at least delta. And if my target is closer than delta, then my movement is going to be x. And delta is not known by robots. It's an arbitrarily small distance that is not known. Now, with those hypotheses, Suzuki and Yamashita proved a very interesting result, which is that we cannot gather two robots in finite time in anything else than fully synchronous. So it fails in semi-synchronous and obviously in asynchronous. without additional assumptions.
What does it mean to gather two robots?
I'm going to define this in the next slide. So that's called the two-robot gathering problem or the rendezvous problem. So what is exactly gathering? Gathering is this idea that we start with two robots at an arbitrary distance, and after finite time, they must be in the same place, mathematically identical place, and not move from there. So if we have two robots, A and B, and they are perfectly synchronized, the only place on the Euclidean plane which they can both be sure the other will understand because they have no common coordinate system is the midpoint between the two. So if they are perfectly synchronized, they're going to target the midpoint and move there. And then they are at the mathematically exactly the same spot. They remain there. That's how gathering happens in fully synchronous. Now, if you have semi-synchronous, which is one robot can be not activated by a scheduler, what can happen is that robot A gets a target, it targets the midpoint. Then it moves to the midpoint, and then robot B is activated. It also targets the midpoint, but it's a different midpoint this time, and so on and so forth. And so the distance is decreasing towards 0. That's what we call convergence, which is weaker than gathering. But the distance never actually reaches 0. It gets infinitely small, but never 0 exactly. So we know that it's not possible to achieve gathering with a stronger scheduler such as semi-synchronous without additional hypotheses. So we're going to talk about those additional hypotheses that allow us to reach gathering. One of the most powerful one was introduced in 2012, which is the lights. So essentially the idea behind lights is that each robot gets a small light bulb on top of its head, and this light bulb can emit a color among different several previously defined colors. It can remember its own color, so it knows which color it is currently broadcasting. And during its snapshot, it knows what is the color of the other robots. And at the end of its compute phase, when it has computed its destination, it changes its own color, if it has to change it. This is basically equivalent to a finite persistent shared memory between all robots in the system. And the result that was introduced at the same time as this model is that if we only have 4 colors, then rendezvous or two-robot gathering is possible in non-rigid asynchronous. So basically the worst possible scheduling. And it also is self-stabilizing, which means that we don't have to make any assumption on the initial states of the robot. So this is a pretty powerful result. And the following year, it was made slightly better by Viglietta, which achieved the same hypothesis, but with 3 colors. So same result with 3-color algorithm. And at the same time, he introduced a 2-color algorithm that worked in non-rigid semi-synchronous. So not quite asynchronous, but semi-synchronous. And we're going to take a quick look at this algorithm so that you understand what exactly light's luminous algorithm means. So essentially, we have 2 colors, black and white. And what we want for gathering is if the robots are synchronized, we want them to move to the midpoint. If they are not synchronized, we want one to stay put and the other to move towards him. And that's exactly what's happening here. If the 2 robots are in the same color and they are synchronized, if they are white, they are going to turn black at the same time and move towards the midpoint. If they are black, they are going to turn white and not do anything. And if they desynchronize, one is going to turn black and the other is going to turn white. And now we have 1 robot in each color. One does not move, and the other moves towards the other. That's how we achieve gathering with 2 colors. Now, this doesn't work in asynchronous because of a very specific and very problematic execution. We're going to talk about this a bit later. A weaker hypothesis that was done using the lights was called external lights. So external lights is essentially the same thing, except robots cannot remember their own color. So they only use the colors of other robots. But everything else is similar. The result is that instead of being finite shared memory, it's essentially finite communication between the robots. And when it was introduced, the result was 3 external color could lead to non-rigid semi-synchronous rendezvous. So with weaker hypothesis, we have a slightly worse result, but it's still a lot better than not having any colors. It is also self-stabilizing. The following year, Okumura introduced to work with to work beyond semi-synchronous, he introduced a weaker version of asynchronous. He introduced actually two weaker versions of asynchronous, which is the LC atomic asynchronous, which is asynchronous, but when the look and compute phase of each robot are atomic, meaning we cannot start the look phase of another robot where the look compute phase of the first robot is still going on. And he also introduced the same thing for move atomic asynchronous. So essentially, if we were talking about registers, asynchronous is regular register for both color and movement, well, position. LC atomic means we have atomic register for color, and move atomic means we have atomic register for position. Using this weaker asynchronous scheduler, Okamura proved that we could have, using 5 external colors, non-rigid self-stabilizing gathering, using 4 external colors, only non-rigid gathering, but not self-stabilizing, and with only 3 external colors, we could have rigid, not self-stabilizing gathering. Now we're going to come back quickly on the Twocolor algorithm from Viglietta. So we know this algorithm works in semi-synchronous, but it doesn't work in asynchronous. And what we did last year was slightly modify it to actually work in asynchronous, and that is our version of the algorithm. The only difference being, if the distance between me and the other robot is 0, which we can do because it doesn't require a common unit of distance, then we do nothing. We don't change color. And this actually makes the algorithm work in asynchronous because we prevent the weird problematic execution from Viglietta. In terms of complexity, however, it's a bit worse. So the best we can do for a gathering algorithm is that the robots only move a distance of x, and they are only activated at most x over delta times. With this Twocolor asynchronous algorithm, our worst distance is 3x, and our worst number of activation is x over delta plus this term can essentially get arbitrarily large. It's not infinite, but it can get arbitrarily large. While this is actually achieved by the 3-color algorithm from Viglietta. So our algorithm is slightly worse in terms of complexity. However, that was not the bad part about the algorithm. The problem is that proving this algorithm showed very challenging, and common method of proving it could not be applied easily. So what we did is exhaustively explore all possible configurations of the algorithm. So that means that we draw out essentially every possible configuration and look, is it going to gather or is it not going to gather? And you find that every possible configuration is going to gathering. The problem is that the proof looks like that. So I'm not expecting you to fully understand it, but essentially that's the part that makes us win against Viglietta. When this was submitted to ICD-CN, so this was accepted, but there were some pretty interesting remarks that were done. This seems to make sense. This is very demanding on the reader, and this is a job for a computer. That's the reviewer too. This is obviously true, and that's what we did. So that's a job for a computer, so let's have a computer do it. The problem is that modeling and doing model checking on continuous gathering algorithms is a bit complicated for basically 2 reasons. The first one is that we said the scheduler has to be fair. And fair means it can forget and not activate a robot for as long as it wants. As long as it activates it at some point, there can be an arbitrarily large number of activations of A between 2 activations of B. And we have to restrict this. Otherwise, the number of states we have to explore with the model checker could get arbitrarily large. The other problem is that we are trying to model continuous space. So the 2D Euclidean plane needs to be discretized at some point because we cannot model a plane using a computer. So for the first point, what we did is we realized that for an n-color algorithm, essentially the fair scheduler can be modeled as an 8n fair scheduler, so meaning we can restrict it to have only 8n activations of a robot between 2 activations of the other robot, which we actually proved in the paper. Next, we have to model continuous space. And to achieve that, we found a very interesting result that any self-stabilizing rigid algorithm actually also works in non-rigid. So that means that if we want to verify non-rigid algorithm, we just have to verify rigid in case of self-stabilization. And when we're checking rigid, then we can just restrict the space to exactly two states. Distance equals 0 and distance is superior to 0, because if we have a target, we are going to reach it, so regardless of the distance between the two robots. So the distance actually doesn't matter to properly model the configuration. Now we also find another interesting result when trying to model self-stabilization and put it in the model checker, which is what I call the oblivious catastrophe. So it is commonly considered that oblivious robots are inherently self-stabilizing. And that is because they have no memory. So if we had an arbitrary initial configuration that had problems, we would eventually forget about this initial configuration because of the obliviousness of robots. Now, the true definition as oblivious is the input of the compute phase is only the last snapshot and nothing else. And it is commonly considered that this also implies that robots have no memory. This is actually true in fully synchronous and semi-synchronous, but unfortunately asynchronous is a lot harder than that. And it doesn't work in asynchronous. So what we have is an emerging property of memory in the system because of the asynchronous scheduler. And to prove that, I'm going to say, let us assume that so we can't do gathering in asynchronous for oblivious robots. We know it doesn't work. So let us assume a slightly simpler problem, which is trying to reach a line and stay on this line for two robots A and B. And the algorithm we want to consider is move to other. So just see where the other robot is and move towards it. And this should work. The robots should never target anything outside the AB line. So they should infinitely stay on the same line. The problem is, because of self-stabilization, we could have initial configurations that include pending targets, and that could be anywhere on the plane. So if we assume that the first configuration that we look at, B as a pending target at point P1, then we execute A does a look, and it gets a new target, which is B, because that's the algorithm move to other. Then B moves towards its target, and what we have is the exact same configuration as the starting one, only with a bit of symmetry and rotation, but we don't care about that because we don't have a common coordinate system. So this will not work. This algorithm for this problem will not work in self-stabilizing, but it would work in non-self-stabilizing. So this hypothesis that oblivious means self-stabilization is wrong. And we had to account for this in our model checking. Now the model checker worked, and these are the results we got. So I introduced most of the algorithms we see here. The only thing I didn't introduce was the centralized scheduler, which is essentially we execute robot A, then robot B, then robot A, then robot B. And the results are all pretty much what we expected from the literature, with two exceptions. Okumura 4 colors and 3 colors are not supposed to work in self-stabilizing. And they actually do work in self-stabilizing in centralized, which was surprising, but looking at the structure of the algorithm and the counterexamples that existed for self-stabilization, it is not entirely abnormal, because the counterexamples rely on simultaneous executions of the two robots, and that's not legal in centralized. So that is about how to use lights for solving the gathering problem. There are actually other ways to solve the gathering problem, or the rendezvous problem. Using lights essentially goes against this hypothesis of no communication and no memory for robots, that we are slightly going against that. Another way to solve the gathering problem is to go against this hypothesis of no common coordinate system. So what has been done is use compasses. So compasses give you north, and they give you right-left chirality. So we know that rendezvous is possible with consistent compasses, so they always point towards north. They also work with eventually consistent compasses, so they essentially point towards anything for an arbitrarily long time, but eventually in finite time they point towards north. They work with inaccuracy, so they have a bounded error of an angle phi. And in that case, if the compass is fixed with an error, so essentially if it has an offset, then it works. We know it does. If it's semi-dynamic, so the error can change, but only between the cycles of two robots, it mostly works. And if it's fully dynamic, meaning that the error can change any time during the execution, we know it doesn't work, that gathering is not possible. That's basically the table of results of what is possible or not. There's still an open question between pi over 6 and pi over 4 for an error. But otherwise, we know where it's possible and impossible to achieve rendezvous with compasses. So to conclude on that, about rendezvous and, two-robot gathering, it's essentially a benchmark. It's to show how difficult it is to achieve anything with this very simple robot model. It's not an easy benchmark. As we saw, we need pretty strong hypothesis to actually achieve things. We also saw that asynchronous is really hard. Asynchronous is a lot harder than semi-synchronous or even LC atomic or move atomic asynchronous, because asynchronous is essentially no atomicity anywhere. And the last thing we saw that lights are pretty powerful because we can actually achieve this hard benchmark in this really hard scheduler using only 2 bits of communication and memory between the two robots, or 3 bits of communication. I didn't say, but we could also, there is also a model called internal light, which is the reverse of external light when we only have memory, essentially. So thank you for your attention. And I'll be taking questions if you have any. It was a lot faster than expected. Yes?
I have a question about application. Can you give some application of gathering of two robots in which kind of problems in real life could we encounter this kind of problematic, and so what you are studying is interesting to solve the problem?
In real life, gathering is mostly a benchmark. It's in real life, convergence is mostly sufficient because robots are not dimensionless, and if they get closer to each other, they're eventually going to collide. But it's sort of a very similar problem to consensus, that we see that if robots are not even able to agree on a common point of destination, then we know that harder problems are going to be completely impossible. So gathering is kind of, it's the basics of what we need to do to be able to achieve anything else, because it's a very simple problem that is actually really hard to achieve.
My question was more about practical problems.
Practical gathering problems.
That can be modeled with the gathering of two robots.
I don't know of one that is actually used in real life. I don't know. Do you have one, Sebastian?
You could say that you want to gather robots in order to update the system, or you have a range for submitting a new program, or you just want them nearby.
Yeah, but
you don't control them. But as Adam said, convergence is sufficient.
Yeah.
The problem you have is that, for instance, in asynchronous, even convergence can get really tricky because the distance can grow, then shrink, then grow, then shrink, and you're going to have robots passing in front of each other. So having an algorithm that, like the Viglietta Twocolor, kind of prevents that. Robots are just going to optimally move and not switch positions or do things like that. That's why just convergence may be not sufficient. Yep.
I'm curious about, so you presented problems mostly in 2 dimensions.
Yes.
And what about a third dimension? Make everything really harder?
It makes proofs really harder. I know of a few papers that tackle 3-dimension gathering. You have, at this point, you can have like lining up, which is a first thing. I know of a paper that introduced, that had 3-dimension, but the robots knew what the z-axis was. So they knew what was the top and the bottom, and they could use this to perform some sort of gathering. But just three-dimensional gathering, it's really mostly going to make the proofs really harder, not really the algorithm.
When you prove with like stronger assumptions, like in really fully synchronous and self-stabilizing.
Well, for two robots, 3D doesn't change anything because the only dimension of the problem is the line between the two robots. So for two robots, it doesn't change anything. But for more than two robots, it's going to change because you're going to have different planes of movement for different sets of robots, and makes things a lot harder.
Yeah, the equivalent problem in 3 dimension is plane construction.
Yes.
So we're agreeing on 2-dimensional space.
And then you can try to perform gathering.
Do you know if this kind of problems can be applied to applications where you need to keep a constant distance between
a constant distance? Without additional hypothesis, it's not possible because robots don't know what distance is. They don't know what's a meter. They don't know that kind of thing. So you would need to add a weaker hypothesis so that the robots actually know distance. Then you could try to work on different algorithms. But yeah, it could be used.
Some real applications is two robots trying to hold some object. So
yes.
They have to move towards this object to two points and then to hold it and move.
It probably could be a similar application because, but at this point you're not necessarily trying to get the robots at a distance. You're trying to get them at a specific point, each one, and then they have to have a common coordinate system. So that's a different set of problem. But it's also a problem that is studied. It's just different from this one. Okay.